Hello everyone. Today we're going to look at the last section of our electric circuit unit, which is called electromotive force or terminal voltage. Now, what we're doing today is going to be all based on one thing in the circuit, the battery itself. Now, up until now, we look at battery as the source of potential difference, as the source of voltage or electrical energy. When the battery is not connected to a circuit, there is a potential difference or a energy difference between the two terminals. And when you collect it, however, something is going to change. Now, the voltage that you can get from the two terminals of the battery was a long time ago termed electromotive force. Now, or in short, EMF. So in here, the E that we use is actually not the English E, is the Greek letter E, so EMF, or sometimes, in short, just this, right? So this is also the same as voltage, okay? Just another way of representing voltage. Now, why is it called force? So even though the name of this, the energy difference between the two ends of the terminal, even though the name says it's a force, it is actually just voltage. Now, and the reason why we are calling it electromotive force is because long time ago, people thought, hey, the electrons are being pushed out of the battery to do some energy delivery, right? So there must be a force pushing it. Now we understand that, yeah, sure, there is a force. The force is called electrostatic force. Remember, one of those forces, four forces that are essential to the building of our reality, right? The gravity, electromagnetic force, and we also have nuclear strong force and nuclear weak force. Now that we know the force that people were referring to back in the day was not really a force, but just the voltage. So it's not actually a force, even though it was called force for thousands of years. So we used to call voltage electromotive force. So therefore, if you look at a lot of old textbook and old study, you will still see people referring voltage to electromotive force, which is EMF, or just simply this simple E right there. Now, so for example, a car battery has a EMF of 12 volts. Now you can see in here, because sometimes it's hard to type the Greek letter E instead of the epsilon, right? There's actually epsilon. It's called epsilon, that little different looking E. So sometimes you see books just typing the regular E, so that is a bit easier. So for example, a car battery, right? The battery that's inside a car that powers the AC system, powers the dashboard, is run by a 12 volt EMF lithium ion battery. And if you take the battery of, for example, like a cell, like a dual cell that you buy, like those battery has an EMF of 1.5 volts. You can see it right on the package. For example, if you use lithium, which is the most commonly used material to make battery, those batteries are always 1.5 volt. So then you might say, Mr. Chang, how come I can buy, for example, batteries that are 9 volt? If you open a 9 volt battery, you'll actually find 6 tiny 1.5 volt battery inside. They put 6 of them together in series, so the voltage add up to 9 volt. So you see lithium ion battery that you can buy is always has a voltage as a multiple of 1.5, because every lithium ion cell chemically is 1.5 volt. You can only make them to be 1.5 volt. Your chemistry teacher in chemistry 12 will be able to tell you more in detail. We're not going to go over that in here. The reason why it is 1.5 volt, not 1.4 or something like that, right? So, but this is only the voltage or the amount of energy in the battery if the battery is not connected to anything. Now, once you actually have the battery connected to something that are using the energy, however, the energy you get from the battery drops. So the energy that you're actually getting from the terminals of the batteries, now the two terminals, right, the positive and negative terminals, is always less than the EMF. So the way I look at this is this way. So the company that makes the battery promise you're going to get 12 volt. But when you actually put your battery in a machine and you try to test out how much energy is coming out, you always get less than 12 volt. So for me, it's like just a little bit of false advertising. Or you can say that, the number that the company are advertising is the ideal number in the ideal situation with no friction. Just like how we always assume that acceleration due to gravity on Earth's surface is 9.8 meters per second. And we know that's not true with air. And there's air everywhere. But the ideal situation will be 9.8 meters per second squared going down, right? For accelerations near the surface of the Earth. So we're using that value. So you can look at the EMF reading of a battery the same way. The EMF reading of a battery is the theoretical maximum that you can get from the battery. But that's only when the battery is not even being used, which is technically never. Because, unless when you're storing it, the battery is not being used. Otherwise, in any other circumstances, why do you need a battery if you don't need to use one? Right? So the moment that you actually put it in your remote control, in your phone, in your computer, you're not getting that theoretical maximum. You're always getting a little bit less. Now, it's like when you buy, slacks, or when you buy, okay, one thing, right? Have you ever eaten instant noodles? The package, the instant noodle package always shows you this like really nice bowl of noodle with all the ingredients on top. And when you actually open the instant noodle and you make it yourself, you just get the noodles, right? So you don't have all those ingredients on top. You have the favorites of those ingredients. Hopefully you do. But you don't really get the real thing, right? So there are two voltages from a battery, okay? One is the ideal number that's printed on the advertisement called the EMF. And the other one is the voltage that you can actually use, which depends on what you actually collect to the battery itself. Now, but this is not just false advertising on purpose by the manufacturer, though. This is actually due to a physics limitation. Because think about a battery. What is a battery made of? Copper, other type of metal, lithium, if you have lithium-ion battery, copper battery, if you have copper nickel inside. So a battery is made of metals, right? Batteries are made of metals. That means it has resistance. The battery itself has resistance, isn't it? So we always draw the diagram like the battery is this one thing and the wire is this one thing, and then the light bulb and the resistor connected to it are all separate things. But in reality, even the wire has resistance because the wire are made up of copper. The resistors are made up of carbons and other materials, sometimes silicon, some other time, which has resistance. For example, a light bulb, the filaments inside are made of, I think, cesiums, which has resistance. So everything has resistance, right? Everything has resistance. Something has more resistance than other material. For example, wood will have millions and millions of ohms resistance per every square meter, per every meter, but like copper will have like a couple hundreds of ohms per meter. So everything has resistance technically. Electron leads to fight through the material, and when they do that, they drop energy into the material and make it harder, make it raise in temperature. That's energy lost due to heat and frictions, right? So, well then, when the battery is hooked up to a circuit, now you have electron going through it, right? Remember, the battery is like Pizza Hut. So you have to have those pizza delivery boys and girls going into the battery, pick up pizza, and go out. So this process itself tells you that there are electrons going through the battery. And if there are electrons going through the battery, and the battery are made of metals, which does have resistance, well, anything has resistance, then that means when the electron goes through the battery, it will lose some energy too. Okay? So that means battery actually has internal resistance. And that's our focus for today. Internal resistance. Okay, so now let's look at a battery. Okay, so let's look at this. We'll go back to that little two boxes on top, but let's go to this. Let's consider a battery. Now, in most circumstances, we will draw like a light bulb or resistor on one side, and we'll draw a battery on the other side, right? Now, don't draw this part yet. Don't draw this part yet. This is usually what happens, right? But in reality, the battery is more like this. Okay, the battery is more like this, where there is a little bit of resistance inside. Now, the resistance inside is usually quite small compared to the rest of the circuit. But of course, if the rest of your circuit has very low resistance, for example, you forgot to hook up the wire to something, so the wire just running back to itself, then that internal resistance is not small. So where's the internal resistor? Right here. It's not like they actually put a resistor inside. I have to stress that very, very carefully. No one do that on purpose. The internal resistance is there because the battery is made of materials. Any material has internal resistance. Now, so where's the EMF and where's the actual voltage? The EMF is the battery that you would get if there were no internal resistance, which is impossible. Okay, so now you have a system that there are two resistors, two type of resistor value. So there's one resistance value, which is the external resistance, big R, and there's an internal resistance value, which is small r. That's due to the material of the battery itself. And the EMF, which is denoted this. Now remember, the EMF is the promised voltage. For example, like a AA battery will be 1.5. But that's not what you will get if you actually measure the voltage drop on the resistor. I mean, ideally, you get 1.5 volt drop too, right? But instead, what you actually get most of the time is like 1.49, not 1.5. Okay? So if you actually take a voltmeter and you try to measure the voltage that's coming out of the battery directly, now, of course, you cannot get inside the resistor, right? Inside the battery, I mean. You cannot get inside the battery. You can only measure it from the outside. So if you get a voltage meter and you try to measure the voltage, what you will measure instead is terminal voltage. Okay? So what you will measure instead is terminal voltage. So you won't be able to measure the EMF because the electron loses a bit of the energy when they are already inside. So the way I look at it in our Pizza Hut model, right, is that you have to feed the people who deliver pizza for you. You have to feed them, right? So imagine that you give them 10 pizza and they only deliver 9.8 pizza. You have to be okay with that because they are hungry too. Right? And you're not paying them anything else other than giving them food. You are a very terrible boss. Okay? You're only paying them with food. Well, then let them eat some of the food, right? So think about that. The EMF would be 12 volt, 12 pizza, right? So I send out 12 pizza. But how many pizza get to the customer? That means if I stop the delivery guy before and after they enter Pizza Hut, you will find that they only have a difference of 11.8 pizza or 11.9 pizza or 11.7 pizza. Why? Because the pizza delivery guy immediately after getting the pizza from you say, well, I don't want to eat outside. I'm just going to take a slide right now or two and then I'll deliver the rest. So even before they walk out of the restaurant, which is the battery, they already consume like a point something of that pizza. Okay? Hopefully that makes sense. Now, and there's one funny thing though, which is conceptually funny thing, which is the amount of pizza that the internal resistance will eat. That means the amount of voltage drop by the internal resistor is going to be actually dependent on how hungry the customer is on the outside, which is the big resistor on the outside. If the big resistor on the outside is huge, then the internal resistance, the voltage drop on the internal resistor is going to be small. So for example, if the outside resistor is really, really big, then the pizza delivery guy can say, well, that customer is really hungry too. Maybe I shouldn't eat too much. I'll just take one bite out of his pizza and deliver the rest. So you get like 11.999 votes delivered to the customer. However, if the outside resistor is very small compared to the internal resistance, for example, you forgot to actually put a resistor in there, so the wire just keep running through, just a straight wire runs through, so that means you're basically getting the resistance from the wires only. Then in that case, the internal resistance could eat most of them, because the pizza delivery guy can say, well, my boss want me to deliver this 12 pizza, but that guy isn't really hungry, so I'm going to eat like 11 of them and just give him one. This actually happened. The larger the external resistance are, the less the effect of the internal resistance will be. Okay? So, but if you put a very small external resistor on the outside, then the internal resistance effect is going to be drastic. Okay, so from this tiny battery, now as you can see from there, so this is the internal resistor, which will have an internal voltage drop. Okay, right? It will have internal voltage drop. So how much is the internal voltage drop? So this internal voltage drop is going to be V equal IR, Ohm's law, right? What I? Well, of course, I total, because this is a series circuit. There's only one path. And which resistor? The tiny one. So that's the internal voltage drop. Okay, so how much are you going to get when you measure the terminal voltage then? Okay, think about it this way. So let's say internal voltage drop is 0.5, EMF is 12. So how much do you get to leave the shop after the resistor eat its own share already? 11.5, right? So that means the equation for terminal voltage is now ready. So terminal voltage. How much energy are you actually going to get delivered to the customer outside, to all the resistors outside? That's equal to how much they promised you minus the amount of current, the amount of voltage that's consumed by the internal resistance, which is this part right here. So whatever that's remaining that's not consumed inside the battery will be used outside, right? So now, in this equation, that is measuring volt. This is measuring volt. Well, technically, the last thing is measuring volt too, but it's, ampere times ohms, which is also volts, right? Okay. So now, so the E in that equation is the EMF, is the promised voltage, electromotive force from the manufacturer if the battery is not being used. The IR part is the internal resistor, internal voltage drop. Internal voltage. That means internal pizza consumption, right? So you have to feed the people who does a job for you. You have to feed them first. Okay, now if the battery is not connected to the circuit, then no electron needs to come out. If no electron needs to come out, then the terminal voltage would be equal to the EMF, because then the second part IR will be 0, right? So if you're not connecting the battery to anything, then the electron doesn't have to travel. If the electron doesn't have to travel, you don't need to pay them. If you don't need to pay them, then the voltage you get from the battery is exactly the same as how much you produce, because no electron is coming out and eating stuff. Yay! So, now chemically though, however, over time, the internal resistance actually builds up, because as the material get older, the metal get older, it will get rust, for example, and rust, right? Because the metal surface is exposed to the air, and eventually every metal will rust at some point. So the more you use the battery, the more its internal resistance actually build up. And so a battery is dead. It's considered dead. When you say, oh, the battery is dead, it's actually what's happening is that the internal resistance, internal resistor inside build up so much that its EMF is now completely consumed inside the battery. That is when the battery is dead. Okay? So when a battery goes dead, what happened is the internal resistance. okay, builds up over time. So the internal voltage drop builds up over time. And eventually, the internal voltage drop is as big as the EMF. So that means the resistor are getting hungrier, the electrons are getting hungrier and hungrier. So you give them chow pizza, they ate all of them, and nothing goes to the customer. So now you consider the battery being dead. Okay, so that's why battery has expiry days, right? Because even if you just leave a battery untouched, it will eventually build up. I mean, slower than if you use it, of course, but eventually the internal resistance build up because rust gets in. Unless I think if you do it in vacuum, if you keep everything in vacuum, no air, no water contact, then the rusting process will take like ages and you won't notice the voltage drop. But I think it's almost impossible to replicate that on Earth. So a battery live it on its own after like 5 years usually doesn't even work anymore. Okay? Not guarantee, but most of the time it doesn't work anymore. So that's why old battery that you find at the bottom of the drawer usually doesn't work. Yeah. Okay. Now, so when you do a question now, you have to pay attention to the fact that there are two types of voltage now. Is the number that give you the EMF, or is the number that give you the terminal voltage? So in here, example, 12-volt battery has an internal resistance of 0.022 ohms. Usually the internal resistance is really small, right? What is the terminal voltage? Okay, so that means this is the EMF. This is what the manufacturer promised, and not what we actually get though, right? Current is 3 amp. Okay, so that's I total. Okay, cool. So this is a direct application of the problem. So terminal voltage is EMF minus I total R. EMF is 12 volts minus I total, which is 3 amp. Multiplied by 0.22 and 12 amp minus a 12 volt minus, okay, so let's take a calculator. We don't need one. 0.66, right? So out of 12 volt, now you can look at it from here. The battery internally, the electron will eat 0.66 of the voltage before delivering the rest of it. So how much can it actually deliver to the rest of the circuit? 11.34. So as you can see, usually it is not a very, very big loss, but it's still like noticeable and significant enough that you have to pay attention to it. Okay, so the voltage is going to heat up the battery, right? I mean, what is the 0.66 volt doing? Like, you have to think about that. Like, what is using? Like, so the electron ate it, so what? Right? So I mean, the energy cannot be destroyed, remember? So this missing energy, remember, like why are we talking about energy when we look at voltage? Because what is voltage? It's the energy carried by the electron per coulomb. So voltage is energy. It's just how much energy is on the backpack. It's inside the backpack, right? So what happened to that 0.66 volt? Well, it's now converted to heat and heating up the battery. Okay, so now we can look at the okay, so now we can look at charging. Oh, so that's actually one extra thing I want to have you look at first. Okay, so please look at this circuit that I'm drawing extra. So this is a light bulb A. And this is another light bulb B. Okay, so circuit. So light bulb A, light bulb B. Now, when the circuit is open, is closed, everything is running good, and you will have like light coming out from the two light bulbs. Perfect, right? Okay, so my question to you now is, what happened if I accidentally dropped a metal bar here? Okay, so I accidentally drop a metal bar here. Or like a copper wire. Or my screwdriver when I'm trying to fix this light fixture. What will happen to the brightness of the two light bulbs? Okay, so think about it. This question is a lot harder than you think. Think about it, and Okay, so now I assumed that you have thought about it. So what will happen to bulb A and what will happen to bulb B? Okay, now a lot of you is going to notice that light bulb B is probably going to turn off. And then it's a little confused about what happened to light bulb A. Now, first of all, let's talk about why light bulb B turns off. Because, you see, when the electron arrives at this junction, it can now go either down or right-hand side, right? So the current can either go down or right-hand side. Now, but remember though, which way would the current go, or how much electron go through which path, depends on the resistance of the circuit. So if you compare the yellow path and the blue path, right? The blue path offers very low resistance. Now, let's assume that this metal is like a perfect piece of wire, has zero resistance. Then this light bulb, of course, is not a perfect light bulb. There's no perfect light bulb. This light bulb obviously uses energy, obviously has resistance, right? So when you compare two paths, one path with like zero resistance, the other path with, let's say this light bulb has like 100 ohm of resistance on it. Then, which path will most of the electron actually go? It turns out that 99.99% of the electrons are going to go blue, like this way. And almost no one goes yellow. So light bulb B won't even turn on. Okay, light bulb B won't even turn on because no one. Like when you, imagine that you have like, that you're going out and then there's like a traffic jam. You can either go down to the green. So you arrive right here. Now you can either go to the right hand side and then go down, go through the light bulb, or you can go directly down from the metal, which offer zero wait time. So you're going in, you're lining up for a theme park, right? There are two lineup. One is yellow. The wait time says 300 minutes. The other one has color blue, and the wait time says 0 minutes. And let's say there are like 100 of us right now. How many of us will go to the 300-minute wait time lineup? None of us. Okay, that's just normal normal behavior, right? None of us is going to the 300-minute lineup. Everyone is going to go through the blue one. So no one will take their energy and go to the 300-minute lineup, which is the yellow path. That means that light bulb won't even turn on. Okay, if you're comparing a path with zero resistance with a path with any resistance, then zero resistance always win. Like, why would anyone go to the path that actually has a wait time when the other path doesn't? Like, it's zero. Now, of course, in here, I know we're talking about theoretically, right? In real life, even a wire has resistance. It has like very little of them. So, for example, like a copper wire that's a couple of inches only has like a few ohms, compared to a light bulb, which could be like 1,000 ohm. So the ratio of electron going through each path is going to be 1,000 to 1. Effectively nothing. Okay? Now, so light bulb B turns off. Hopefully now you agree. But what is surprising is light bulb A. Some of you might say light bulb A gets brighter. Some of you might say light bulb A gets dimmer. What if I tell you light bulb A also shuts off? That's the surprising part to a lot of people. Now, so again, this time, let's look at a junction. The junction here. So in here, the electron, look at it two-way. I can either go down or I can go to the right. Right? The electron look at it this way. So when I go down, I will go through this green pathway. If I go to the right, I'll go through this blue pathway. You will notice I don't have to go through the last light bulb, right? Why would you? 300-minute wait time. Don't even go there. Right? So the electron is now looking at this two pathway and say, okay, if I go through light bulb A, for example, this could be like 200 ohm, 200 minutes wait time. Or I can go blue, which has 0 wait time. Where would I go? 200-minute wait time or walk like an extra few steps. Remember, electron travel really fast inside a circuit, so that extra sections of wires, nothing. So again, you're gonna get like almost 100% of the electron going to the blue one, and almost 0% of the electron going through the green one. So by dropping that wire in there or the screwdriver in there, you are effectively making a short circuit. What is a short circuit? That means, look at this blue pathway. Almost 100% of the electron are going to take that blue pathway. I hope you agree with me at this point. Wait, who is eating the pizza? Let's say this is a 20-volt battery. That's your V total. Who is eating then? Light bulb A shuts off, he's not eating. Light bulb B shuts off, he's not eating. They're both not receiving any pizza, or very little amount that they don't even light up. Who is eating the pizza? The electrons are. Okay? Whatever the tiny little bit of resistance on those copper wires are. That's going to be a big problem. Because remember, when the internal resistance eats energy, consumes energy, what does the energy actually do? It's generated as heat, right? Dissipated as heat. That means it's going to heat up the circuit. It's going to heat up the battery itself. And in a few moments, the battery is going to turn into a very beautiful firework. That's what's going to happen. The wire will be red hot. The wire will look orange and grow. And the battery will start smoking and burn. Now, if you want to see a real example of that happening, please look at the Samsung Galaxy Note 7. The cell phone that exploded when you're charging it. That cell phone has exactly this problem because the battery was faulty and there were some part in the battery that will accidentally touch parts that they should not be touching as the charging cycle continue. And creating this short circuit runaway effect where the energy is being fed back into the battery so the battery will heat up, expand, explode, and injure people. I remember that a few years ago when the incident happened, I think there was a game online that actually made the Samsung Galaxy Note 7 as a weapon in the game. So you can throw it instead of a grenade. Like you throw a Samsung Galaxy Note 7 at the enemy and it explodes like a grenade in the game. That was pretty funny. I don't remember what game that was though. But that's the danger of not knowing physics when you're trying to fix electronics, right? Like just by dropping that wire there by accident, you are creating a fire hazard that could potentially burn down your house. Now, this is talking about one battery, which has limited amount of damage that it can do. But if you did something stupid like this with your house electrical wiring, that's why you hire professional people to do the wiring at your house, right? Because if this happened to one of your wall sockets, the amount of energy is so much greater than a battery, it will burn down your house. So you don't fix your own in-wall wiring unless you have a electrical license or unless you are Mr. Chang, which knows enough about these stuff and have been teaching these stuff for many years and fixing his own stuff for many years. Okay? You hire someone who has a proper license when you want to install a new, for example, outlet on your home, inside your house, right? You want to install, like, okay, you don't need to hire someone professional person to change a light bulb. You don't need to do that. But what if you want to put another light bulb, slot on your ceiling, right? Like that, you need to hire someone who does it professionally. Because what happened when amateur do this? Like this happened. Okay, when amateur does this, wires not being careful when they are managed, right? When they're tangled together like this, sometimes when certain part of a wire touch other parts of the wire that they should not be touching, you could create something like this. It's very, very hard to actually catch it before it starts burning. It's very difficult. Now, I'll tell you a little story. When I was in high school, Physics 12, I believe, 1 year we were doing a lab. And when I was in high school, okay, so I was a student in that class. And my friend who sit next to me during one of the circuitry experiment actually created a little explosion. And that was really scary. Yeah. And I was sitting next to him. I was doing my own experiment, collecting my wiring. And he was doing his own stuff. And suddenly I heard this like hissing noise. It's like tss, and it was one of the battery expanding so much that it is bursting out, and then it, it exploded. Okay, and he screamed. I screamed too, kind of like, whoa, what's happening? And then the teacher rushed over and then tried to put some sand on the battery so that put out the fire at least, right, to begin with, right? But so this really dangerous. It's really dangerous. I mean, a AA battery could burn you. Your house with this kind of mistake can go total. Okay? You can lose your house for that. So be very careful. Okay? Now, let's go back. So this time, so just one last thing, which is, so we talk about using a battery. Now we have to talk about charging a battery. So this equation right here, right here, can actually be changed into charging. So when you're charging the battery, you're forcing the electron to take pizza and to put it back to Pizza Hut. It's like loading the stocks on Pizza Hut so that they can sell it again later on, right? Loading the ingredients to Pizza Hut. But you have to feed. Again, you have to feed the people who does the job for you, right? So you think about it this way. So imagine that you're putting stuff back into the battery. So let's say the EMF, you want the EMF to be 12 volts, right? How many volts should you provide on the outside charging this EMF of 12 volt? You must put more because you want 12 pizza to go inside the battery, right? To the EMF. But you have to assume that the electron will eat some. So you give electron 13, for example, and say, hey, thank you for doing this job. Take 13 pizza. I only need 12 of them to go back to the storage. So the extra one is yours. Right? So in this case, the terminal voltage is 13. And the EMF is 12. The terminal voltage is higher than the EMF when you're charging a battery. Does that make sense? So when you're restocking Pizza Hut, the storage room in Pizza Hut is 12 volts, like 12 pizza at a time. But how many pizza at a time do you have to give the electron to move in? You give them more than 12. 12.5, 12.2, 13 even. Why? Because you have to assume that they're going to eat some during the process. I almost feel like we are bad-mouthing electron for the whole hour. Electron is not even a conscious being. We are bad-mouthing something that is just following the laws of nature, like it's doing something really bad. Always have a sticky finger, always stealing from you, eating part of the product that you're selling. I know. But this is an analogy that, actually, the funny thing, I think I talked about it last day, right? This is the pizza analogy was actually created by me. As in, I created it when I was in grade 12. Many years ago, of course, right? I just thought it was funny, and I keep trying to add stuff to it so that the story makes sense. I think I'm at the point where you can actually explain circuitry with just pizza and Pizza Hut and delivery personnel. Almost every concept in there. I thought you find that a little bit more easier to understand. I hope compared to just learning the equations and the format. So the only thing that's changing in this equation is adding, right? The subtraction sign, on top, the minus sign become addition sign. There. Okay, so this is for the battery. So the EMF is how much you want to put inside the battery because you're charging it back up. And the terminal voltage, which is how much energy you have to provide on the outside, has to be larger than that because part of it needs to go to the food for the electrons to eat, which is this part, right? This is the food part. The electron has to eat something. So electrons payment. You have to kind of pay the electron to do the job for you. So this is the payment. So if you want 12 to go in there, you give the electron 12.5 or 12.2, something like that, right? So where this is the voltage needed to charge the battery. Now, on the formula sheet, these two equations are combined to one. So I need you to go ahead and open your formula sheet and make notes of it. So you use the -1 when the battery is being used. You use the positive version if the battery is being charged. Okay, so moving on to this one example, and then this entire unit is done. 12-volt battery. So I want the battery to have 12 volts at the end. And I'm charging it with 15 volts. Okay, which makes sense because, have a bit extra just in case the electron need to eat something. And the internal resistance is 1.3 ohm, so that's more. What is the current through the battery? Okay, so asking for the current. Now, so terminal voltage is EMF plus, because we are charging, I total R. And so we are charging with 15 volts. We actually just need 12 volt inside, but because the electron need to eat some, we are going to provide our extra voltage for the electron to consume. Otherwise, right, no one does a job without expecting some kind of payment, right? The electron expect energy as payment, like pizza. Cool. I total. Very good. So you have a worksheet 7.4. I'll write down the question that you should try. There might be questions that you need to. Okay, so for example, when you're doing a question with like internal resistor in there, for example, like looking at a circuit like this, right? If you need to calculate R total, for example, you have to remember R total is actually R plus small r. So let's say you want to do a voltage drop on the battery, you have to ignore, basically you're looking at this circuit as if that internal resistor is just a resistor. You don't have to look at it separately. So you can say, okay, if you want to do a voltage, Ohm's law on the battery, the Ohm's law on the battery looks like this. EMF equals to a voltage, right? EMF is voltage. V equal IR. So I total, R total. So it'll be like that. So V total, which is EMF, is I total, R total, where R total is big R plus small r. Okay, so like Ohm's law with this type of question, you have to be careful. If you want to do Ohm's law on the battery, do it with the R total and use the EMF. Don't use the terminal voltage. Unless the question asks you for terminal voltage, you almost never have to actually get terminal voltage. Just use the EMF. You can ignore the fact that this internal resistance is an internal resistance. Just treat it as another light bulb right next to the battery. Then the whole question will work out that way. Okay? You don't have to look at it any differently than other resistors. It is a resistor inside the battery. Think of it like that. So what is R total? The outside external resistor plus that inside one. That's the R total. And what is your V total? Well, anything before the drop, the EMF. Okay? Look at it that way. So you have two equations. You can either do Ohm's law like this. Otherwise, the calculation actually looks a bit more taunting. Okay, so electric circuit unit done. All right, I'll have everything uploaded on the course website, including like any extra information that you might need, and then see you next class.